will be done by Professor Deepankar Choudhury. Currently, he is Institute Chair Professor of Civil Engineering at IIT Mumbai. But I can call him as a national IIT professor because he also had opportunity to work at IIT Kanpur. And on deputation, he was also at IIT Gandhinagar and Dharwad. And he also makes his career international because he had been involved with visiting faculty fellow at NUS Singapore, UOW Australia, UC Berkeley, Gokashima University, TU Darmstadt, and Incheon National University in South Korea. This gives us a overview of Professor Deepankar Choudhury, and we'll be happy to listen to him sharing his experiences from these and much work he has done earlier. His basic areas of research are geotechnical earthquake engineering, computational geomechanics, soil structure interactions, sustainable foundation engineering, and soil dynamics. And he has developed himself a new concept of pseudo-dynamic method. And this is going to give us also a help in earthquake-resistant design of geostructures. And this is becoming increasingly popular throughout the world. Even as a young researcher, his work was recognized by getting considerable number of awards through INSA, through NASI, through ISCA, through INAE, through IEI, DST, DAE, ISTE, and from abroad also. So he has a very distinguished startup in his after his PhD, which he continued at many institutes of India. And he has, of course, widely published in many journals, national, international, and is I should say, a very fond speaker to all of us. Wherever we go, we always like to listen to him. He is involved with several mega projects of national and international importance, and a member of various code committees of India and abroad. But more than anything else, actually, he's also serving the IIT administration and being closely involved with both JEE and GATE, which are prestigious to IIT itself, actually. He received a number of awards for his own PhD and also for his students now, and of course recognized at IIT Bombay itself with the Professor S.P. Sukhatme Excellence Teaching Award in 2017. He's a very excellent speaker now. We are eager to hear you, Professor Deepankar Choudhury, on the solutions for foundation systems subjected to earthquake conditions. Professor Deepankar Choudhury.
Namaskar, everybody. Thank you, sir, for your kind introduction. And I hope that all of you are staying safe and happy in this difficult time. This is missing everybody to meet in person during this IGC, which usually we do. But nevertheless, this is another opportunity to find out how we interact through this digital platform. And this year, probably I would not have able to attend IGC if it is not in this online platform. So, and
we're lucky to hear you.
Thank you, sir. Thanks a lot. Let me share my slides. Let me see if it is visible. Is it visible to all?
Not yet.
Okay. I shared it. Let me once again do that. Share screen. This one. Share.
Yeah, it's coming.
Okay.
Full screen now. That's it.
Okay. So is it visible now?
Yeah.
Okay. Okay. So thanks once again. My gratitude to the organizers, and thanks, Chairman Sir, Professor G.V. Rao, for your kind words. And it is my immense scholar and researcher, Professor Madhavushi. We work on the similar area. And today morning also we heard the 42nd annual lecture by Professor T.G. Sitaram, and his research group's exemplary work for 25 years on this domain of geotechnical earthquake engineering. So probably after them, when I'm starting speaking on similar kind of topic, I was always thinking that what is that I'm going to speak in this IGC in the lecture. So I tried to find out some of the case studies which we have executed recently, actually. And those are related to essentially the giving the solutions for the foundation system under earthquake condition. So let me start with this. And first, I want to thank my co-authors. Those are my PhD scholars. Actually, Dr. Milind Patil just graduated recently, and Mr. Shivayan Bishwas and Ms. Sujata Manoj. They are the co-authors along with me for this paper. So they have contributed essentially the project in which they were involved. Those components only I have kept here. Other than that, of course, in my lab, several former and present PhD students are contributing extensively in this major domain of geotechnical earthquake engineering. We all know about the importance of the structure, and we all know that structure, of course, its stability, everything comes when foundation itself is stable. So that is the basic fundamental work. And also we have to make sure that and overcome the challenges regarding the stability of foundation when it comes in the earthquake prone areas. We all know about several failures of structures, mainly due to the foundation failures. And some of the pictures are shown over here. No need for this introduction, essentially, for this August gathering today. And we also know that how the foundation unit actually, it is quite extensive. It is not that only we talk about the building foundation as a geotechnical engineer, but we also talk about the excavation close to the existing structures or buildings, even tunnels, and so many other things also comes under the domain of foundation engineering. We all are aware about it. And the ongoing construction boom of worldwide, we all know that the super tall towers are essentially in the urban cities are a present day scenario. And across the world, this is the increase in the height of the buildings we all can see and aware about. Coming to this, what is called, what are the various challenges we face when we talk about such a very heavy or tall structures? Essentially, of course, its capacity, then settlement, then differential and settlement in terms of tilt, response to lateral load, moments. All these are kind of parameters which essentially we have to take care of as a foundation engineer. When it comes in the earthquake-prone region, then additional parameters like the dynamic behavior of the foundation system, then the earthquake response of the foundation, then structural strength of the foundation elements, these additionally get added in the challenges what essentially as a geotechnical engineer are supposed to provide solution. Now, if we see this various literature are available in actually on the similar topic, I just want to highlight that this book, probably we tried to give all the dynamic response of various foundation system for high-rise structures. One can see through that. Coming to the modalities of addressing this problem of how to address, like whether the foundation or the building or the structure which we are going to have in a seismically low risk area or moderate risk area or high risk area probably is the fundamental thing we need to first identify. Because based on this identification, what are the types of testing we should start, that actually is very important. I remember today in the morning also towards the end in conclusion, Professor Sitaram was mentioning that essentially the geotechnical analysis, design, everything, the fundamental basic thing involves or depends on the major quality testing. So that testing, he actually asked Professor Charles Senji that probably ISSMG can take a lead in the form of the type of the testing what we give. So this is very important as well. when it comes in the form of the seismically active area, because accordingly, whether it is only in situ testing or in situ plus combined high quality undisturbed sample collection and then laboratory testing and site specific correlations, all these are essentially important to address. If we check this curve, actually, this is a classical curve, I will say, given by Atkinson in 2004. This is essentially, we talk about under the dynamic behavior, how the soil properties degrade. That is essentially the shear modulus, what we talk about. The shear modulus degradation is probably one of the major factor, the stiffness degradation during the earthquake. And until and unless we measure or we are actually able to capture this shear modulus degradation properly in our design and analysis, probably we are not doing the correct thing, and that may lead to danger in our structure, whatever best quality design we do. So this is essentially comes on the shoulder of geotechnical engineers or geotechnical earthquake engineer to check actually what type of degradation of that shear modulus is essentially occurring in the range of the cyclic shear strain in which your structure is subjected to, or you want your structure to be subjected to, or you want your structure to design to. So essentially the stiffness parameter, this damping parameters, Poisson ratio, density of material, all these are important along with these things. Now, coming to the various components, essentially in my today's talk, I tried to touch three aspects of foundation system. This is the first case, actually, the first foundation system, which I am actually trying to present over here. Foundation system one, which is pile foundation. We all know about how the pile foundation need to be designed in earthquake prone areas, etc. So I am not going into the theoretical detail of it. What I am trying to highlight here today, that a recent mega project in which we were involved, that project only I am going to tell you how we have addressed or solved this design problem of seismic stability of foundation to support bridges. So as I said that I'm not going to the fundamental details of pile foundation because today's lecture is not on that essentially. So I am going to talk about this project which we handled at IIT Bombay given by L&T, heavy structures and geostructure divisions of L&T. So this is the foundation for the Mumbai Trans-Harbour Link, MTHL. Package one, there are three packages altogether. And remember, this is India's longest sea bridge, which is under construction now, and which will be of the length of 21.8 kilometers. And this is a MMRDA project. And there are various agencies and institutes, etc., are involved. Actually, I heard about in the preliminary phase about this project when I was visiting Incheon National University in Korea with Professor Issy Shin. He mentioned and showed in one of the Korean newspaper, it came that various companies were bidding for this project construction actually. So finally, L&T got it, and L&T Heavy Structure approached me for the seismic design component. So if you see the geographical location of this project, this Mumbai Trans-Harbour Link, this is essentially connecting these two, you can say island. Essentially, Mumbai is composed of 7 old islands, as all of you may be knowing. So this Navi Mumbai and Mumbai, it is connecting, and this will be India's longest bridge actually, 21.8 kilometers. So starting from Mumbai's South Choudhury to Thanik Creek to the north Elephanta Island. And I have visited the site also along with my students, and they have shown this is a beautiful scenario. Actually, you can see when it will be get completed, you can see some part of the Elephanta Cave hill, etc., from this bridge. And this will significantly reduce the traffic of Mumbai and the travel path also. So this actually the architect of present day Mumbai city, actually everyone knows, engineer Wilbur Smith. in 63 itself, he proposed that that time name was Uran Bridge, he told. Uran Bridge actually required for the development of Mumbai. And that time cost estimation was about 96 crore. But unfortunately, over the last 40 years, it could not materialize that project. And finally, the government decided that, yes, it is very much essential for Mumbai. And that's why the new estimated budget, you can see several many folds after those many years. And it is expected to get completed now, 2022. Actually, the pier level construction, all those are done. If you see the soil profile, essentially, which was supplied by L&T to us when we have been asked to do the seismic design. So this is the various layers. You can see the actual depth, very soft silty clay. Essentially, it is the creek region of Arabian Sea. So you can understand the standing water is there. And then you have very soft silty clay, then stiff clay, then residual soil. And in the Mumbai region, as you all know, probably at a relatively shallower depth than other areas like Chennai or Kochi, etc., you get probably the rock at a shallower depth, about 17 to 20 meter or 25 meter, you essentially get the highly weathered basalt and all those things. So now we started to classify the soil in terms of our dynamic analysis, and there we face several challenges. As I mentioned, that the geotechnical testing is not given importance many places, even such an important case also. So they have done only SPT test. So only SPT N value was available. I asked whether they have done any kind of seismic survey test. No, nothing was available. So we have to estimate from available correlations worldwide what are the various shear wave velocity values, and accordingly what can be the IS code wise. The latest IS code actually fortunately gives the classification of the soil based on similar to the NIHARB guideline, that class A, class B, class C, class D type of soil. Then we analyze this MTHL project like into the two parts, like seismic analysis of the site response analysis using the Sheikh 2000. And then we did the entire dynamic soil structure interaction analysis for the complete bridge foundation system using finite element software Plaxis. And as you know, Mumbai is in the seismic zone 3 as per IS code. And these are the 8 earthquake ground motions were actually given to us. This is again, this is developed by NGRI. NGRI actually did the initial seismic ground motion analysis for the site, and they gave the 4 horizontal motions and 4 vertical motions for which the design of the foundation need to be done. So you can see over here what are the various values of PGA, then duration, bracketed duration, predominant frequency, and so on. We carried out this one-dimensional equivalent linear analysis for in Sheikh, and we've identified what is the influence of amplification, because as you know, this is being the creek region and with the very soft clay material, and we all know about Mexico City and other places earlier earthquake disasters. So from that, amplification comes as an important parameter to be considered here in the design, and damping factors, then cyclic shear strain and modulus degradation, which I mentioned earlier. So after all our studies and analysis, we found that maximum amplification of about 2.18 times from the bedrock motion, it is happening, of course, depending on the worst case scenario of the ground motions, what NGRI have developed for the site-specific study for this project. Then coming to the, after finding it out, then the next study is the dynamic soil structure interaction for the entire foundation. Now for this foundation, the design, initial design was done, and they asked us to check whether it is seismically stable or not. So the design is like this. Each of the 2 pier and then pile cap over here, and you can see 4 piles actually, 2 by 2. So 2 by 2 pile actually is for each pier, and pile length is 36.5 meter, and diameter of each pile you can see over 2.2 meter, which is relatively quite large, as you can see. And the piles are connected to a 3.3 meter thick pile cap over here, you can see. And the pile cap supports 2 pier shafts of 15.134 length and the pier head of 3 meter. And bridge deck, finally, it will be resting on this pier head with the help of elastomeric bearing. So that is the design arrangement. You can see after doing all the earthquake analysis, considering, of course, the maximum credible earthquake, MC values, the various amplification factors for different pier locations, etc., has been obtained, and then the critical pier has been designed. And this is under the static case. What are the various displacement? You can see the vertical and lateral. In the seismic case also has been obtained. You can see all the results. These are reactions in the pile, support reactions, axial forces, and we have to check whether all these are within the tolerable limit of the design and the testing, etc. These are the reactions and the bending moments you can see. So finally, our conclusion for this project was like this, like site-specific seismic response analysis, it is carried out and it actually considered in the seismic design. Then one-dimensional liquefaction, one-dimensional equivalent linear earthquake analysis shows that top 16 meter of the clay is susceptible for the significant amplification, and that actually should be considered for the bridge design, and that has been given and analyzed. Then detailed finite element analysis was actually taken care of, considering the dynamic soil structure interaction. And you can see that from the numerical analysis, it may be concluded that the existing foundation system, what has been proposed in the design phase, is able to sustain the earthquake loading of this zone, whatever was been proposed. And with this, actually, we completed and found out that the response of the foundation system also under seismic condition will be in the permissible limit. So with that, actually our proposal was given, and when we went to the site, we have seen that already up to pier level after this they have constructed, and everything hopefully will be fine, and a design life of this is 100+ years. Coming to second category of the foundation system, here we are talking about Barrett foundations. Barrett foundation for tall towers. This I will say kind of relatively newer in the sense like last 10-15 years or so. And there are several advantages of Barrett foundations over conventional pile foundation for very tall towers. So this Barrett foundation, you can see over here the picture over. Just let me, yeah, I'm sorry. Okay, so this picture actually is talking about the Barrett foundations of Hong Kong in Kowloon Station. You can see total number of Barretts in this region is about 290 Barretts of 125 meter depth. And what are the advantages of Barrett foundation? You can see like these are cast in place reinforced concrete columns of square or rectangular shape typically are used. And this differs from the typical circular shape of the pile, and the method of construction also varies. There are several advantages over board pile, like more suited for the tall towers. The major advantage is essentially you are getting the more skin friction components, so higher skin friction for the same equivalent sectional area compared to pile you get in the Barretts. The verticality of the Barretts, actually the tolerance of 0.3% is given, and the group efficiency also is much better in case of Barretts, and there is a significant reduction in the raft thickness instead of going for combined pile raft with piles. So better environmental sustainability because concrete amount of concrete will be less and the cost saving will be significant. I will come to that very soon. So these are various typical geometries of the Barretts you can see, and this shows the construction sequence of the Barrett, like essentially the 3-stage operation: drilling, then placing of the reinforcement in place, and then finally concrete. Here, one case study, actually this is done by Ms. Sujata Manoj, my PhD scholar, and also she's was a technical director earlier in the Dubai Fugro office. Right now she is in Singapore with Mott MacDonald. So you can see the Eurocode 7 essentially suggests that the it allows the results coming from the static load test to be taken, and then Howard-Kenny equation can be used for the ultimate skin friction computation in rock-socketed pile. And similar way for the Barrett's also, similar equations are proposed or considered to be used. So this is the site profile in Dubai. It is essentially for the La Mission Tower. Actually, the Barrett Foundation has been used. You can see the various soil properties of the layers over here. What I want your attention to look over here, you can see the axial capacity in compression versus depth. If you see the comparison between the Barretts of different sizes and equivalent area of the pile of different diameters, of course, equivalent of each of this case, like a red over here, this one and this one. So the dotted lines are for piles and the solid lines are for the Barretts. What it essentially shows, you can see here even much better, the solid line is for the Barrett and this dot line is for the pile. So for a given settlement, suppose if you restrict your settlement and do the serviceability limit based analysis or design, in that case for a given settlement, obviously the carrying capacity of a Barrett foundation is much higher than a similar area or equivalent area of the pile foundation. So this is very advantageous, which I was highlighting. You can see the lateral capacity wise also, the Barretts are much more capable of taking more load than pile foundations. And there is a huge amount of saving of cost because of the saving of the concrete. You can see the cutoff levels and etc. Altogether for this project, actually 14 million AED was saved finally in Dubai for this project in which Sujata was involved in La Mission Tower. So for the details, you can refer to our paper. It is available online, Proceedings of IC Geotechnical Engineering, IC London, UK. It is available online. You can see that how the load cells, etc. were used for this Barrett advantages were analyzed for La Mission Tower. Coming to the third type of foundation, which I am going to highlight here again from our one of the project which we have handled. I am again not going to cover the theoretical aspects or the fundamental aspects over here. So here the stability analysis under the seismic condition for the Cation foundation. So Cation actually is always, since historical ages, Cations are used and it is you can, whenever we talk about the Cation foundation, this is a very popular picture, I will say, in the website available. Probably it took the longest time of construction in Saraighat Bridge in Brahmaputra River in Guwahati because of several issues. Now finally it is complete. And this Cation foundation, we all know about its theory and etc. So what I'm going to talk about here, like we have been approached by this BRPNNL, that is Bihar Rajya Pool Nigam Limited, which is under government of Bihar. They approached us for a bridge on River Ganga in Sultanganj in Bhagalpur district. And so for this bridge foundation, actually, initially, there were two sides always, you know, the owner side and the contractor side. They approached two IITs, IIT Roorkee and IIT Delhi, and there were some difference of opinion. So finally, they approached us for finally come to what is the design philosophy and what implementation in the design they should do. So this is the kind of 2x2 lane bridge in the River Ganga, and now this is complete. Actually, this is connecting between NH31 and NH80 in the state of Bihar. This is the length of the bridge of the 3.16 kilometer. Foundation is 14-meter diameter of well foundations, and number of wells are 45 numbers. This is the location you can see. This is connecting between these two locations, and this is the various stages of construction over there. These are various dimensions of that particular bridge and Cation foundation, actually, which has been shared with us. And we have been asked to check also its seismic stability, because you know the Bihar state actually is in a zone 4 of seismicity, and obviously the seismic analysis also is very important for that. So the mode of shear failure during the bearing capacity calculation, and then the safe bearing capacity arriving at that it was depending on the value of phi, all those things. Essentially, we know I will probably highlight the earthquake component. So the various bearing capacity factor in both general and local shear failure mode, and it was actually the intermediate failure mode. So that's why the proper interpolation need to be taken care of. So this is what I was highlighting, that how it behaves. This is our analytical study. Actually, my one ongoing PhD student, Mr. Shiban Mishra, who is another author of this paper. So he is doing a work on this area, that how this Cation foundation behave under earthquake loading condition. So essentially, this is the three-dimensional wedge, how the passive pressure changes, and in turn that passive pressure, always influence the friction factors when we talk about any such design. So these are the details of the analysis. You can find it in the paper, actually, the details of the equations. I'm not describing those things in this short presentation time. And you can see the comparison of our analytical results with various other researchers' numerical result. And so and there are two extreme conditions, like when you don't consider any side friction and when you consider full friction. And as you know, even recently there was in IGS forum, there were several discussions whether to consider skin friction or not. Essentially, we generally don't consider skin friction, and on the conservative side, we always do. So for that also, you can see what closed form solution or the analytical solution for this 3D wedge seismic analysis can provide from our study. So after this analytical study, what has been done from our lab, Mr. Shiban, he carried out the dynamic analysis also under a different earthquake motion, and he carried out how this behaves, the Cation foundation for that particular region, for what has been asked for us to do. And these are the various soil resistant, normalized depth, etc. So the final conclusion from this project, what we got essentially, like intermediate shear failure mode has been chosen for SBC calculation, and to incorporate the effect of scouring the submerged unit weight of the soil from the maximum scour level to the founding level was considered. Then initially we did the pseudostatic analysis, as you can see, for the Cation foundation, and then later on we extended to Plaxis 3D analysis with dynamic analysis also, including different seismic motion. And from the numerical analysis result, what we found that it can be concluded that the existing foundation system is able to sustain the transverse load coming from the seismic condition from the side. So that was the summary altogether. So if for further details, if anyone is interested, you can refer to our paper. Last year in 2019, this paper came in IC Geotechnical Engineering, London, by Shiban, Seismic Soil Resistance for Cation Design in Sand. And this year, actually in the present issue of iJob ASC paper, you can find out this paper, that Cations in cohesion soil considering 3D wedge effect, what I was describing over here. So with this, I acknowledge, of course, all the companies. There are several who actually encourages us how to connect our theoretical knowledge or the problems with the practical problems or the site-specific problem, etc. So I really thank all the companies, organization, industries coming forward and giving these various challenging projects to us. And I only could talk about 3 of them. There are several others who actually gives us opportunity to explore those things. So with that, I thank all of you actually for joining my presentation, and thank you all. Once again, thanks to the organizers and Professor G.V. Rao for chairing the session. Thank you. Namaskar.